My name is David Russell. I'm the project manager, lead developer / chief software architect for Flag3D here at Itasca. I'm going to be attempting to cover all of the new features that we've added between Flag3D 5.01 and 6. I'm going to warn you, there have been 4 years of furious work adding stuff to Flag3D, as well as features that have been added in the process of developing PFC 5. As a result, there is no way in the time I have here that I'm going to be able to do all of the things that have been added justice. I'm going to hit the highlights. I'm going to move fast. And I'm going to give you places where you can explore things in more detail later. I'm going to assume that none of you have had any experience with Flag3D 6 yet, but you are all Flag3D 5 users. So the first thing I want to see is there have been some user interface changes, and once again, there's a lot going on here, but the most obvious one of which is the control panel, which is now fixed on the right because that's where everybody uses it anyway. You can turn it on and off with a simple click of this button, and here you have control over what we call control sets are in the control panel. You can turn them all on and off. There are many more than there used to be. They are also draggable, so you can order them just by drag and drop. And you can add tabs, so you can have multiple tabs of sets in one control panel associated with a pane if you want. That's just what I'm going to do about the UI for now. Everything else I'll show you as we go through it. The first thing you do when you make a model is make a mesh. So we've spent some time giving you more options for mesh generation. First of all, if you have access to a third-party tool, whatever it is, you can import that mesh from outside, and we've tried to make that easier. Here, for example, you can import using the Flag3D proprietary format, and I'm going to show you some files that were created using Gridle, which is our new standalone mesher that is a plugin to Rhino. We're very excited about it. It is much better than the previous offering called Kubrix. This, for example, is a mesh that was created based on 9 intersecting faults. You can see how it handles all those intersecting planes quite nicely, even down on the inside. Here, also from Gridle, is a salt dome, where you can see how it can handle sort of the kind of irregular mining geometry. And if you look inside, you can see that salt dome created on the inside and the mesh that was created to match it and the various layers and intersects it. We also, however, have added built-in compatibility with both ANSYS and Abaqus file formats. That means that between the two of them, they cover files that can be exported from the vast majority of third-party mesh generators you might have access to. So whatever mesh generator you have and you're comfortable with, we want to make it work with Flag3D. So here's an example of a mesh from an Abaqus format of a control arm. And whoops. Here is ANSYS. Now, the ANSYS compatibility we have tends to come in 2 different files, a node list and an element list. So first you select the node list, and then you select the element list, and then you get your ANSYS mesh. This is something that was created in an ANSYS mesher. Okay. However, that's external tools. We have added much more built-in facilities for making meshes. The old primitive system that was called Zone, I forget what the old syntax is now, GenZone, has been replaced by what we call Zone Create. That still exists. I'm not going to show that because that's basically exactly the same as it was before. And the 2D extruder that was introduced in Flag3D 5 is still present with some enhancements, but not anything I'm going to focus on right now. You'll notice that we can go here to see, this is a simple primitive little cartoon of 2 tunnels. But now we have another option. Instead of extruding this directly to zones, we can extrude this to the new meshing system we have called building blocks, which you can think of as a kind of 3D version of the 2D extruder to help you build structured mesh files. So here now we have a 3D representation of that tunnel, and we can edit it just like we could in the 2D extruder, but with 3D tools to make 3D versions of it. I'm not going to spend too much time doing that now. Again, I don't have time to cover all of the interaction tools we have available to us for making meshes. I can just show you some of the highlights. For instance, we can select faces here and then select all those faces, and then, for instance, build up a new level of that in 3D in one click, and then go on with life. That's if you're starting with the extruder. You don't have to start with the extruder. You can, for instance, just start from scratch. If you go to the building blocks pane and say, now you get a little block here. Now these blocks can be built up sort of interactively. That's what we call the building blocks. You can just keep popping blocks on top of each other, here and here and here. You can even click and then pick what kind of topology you want. Like I want that right there, and it'll fix it. Okay. You can import a geometry record from the background. This right here. So this is a CAD data of a tunnel you might want to be creating. Now you can use that as a sort of a background template for the creation of your building blocks. Again, I'm just going to go through this quickly due to lack of time, but for instance, you can grab this node here and then snap it to data in the CAD. I can pick which intersection or face I want to connect to snap it to that. So here I can do that here too. Go from this to that to snap it to all those. Another thing you can do, for example, is I can select these edges add internal control points to make them curved, and then I can what's called drape. So I can say I want to drape vertically, and that will automatically extend those nodes up until they intersect the surface, including the control points, to conform them to that surface. So you can see how easy it is conceptually to sort of build up blocks and then make it conform to the surface of CAD data you start with, and then move on with life in a topologically connected way. Another possibility for starting to scratch, and this is what I'm going to focus on for the rest of the webinar, is you can start with what we call a template. So here is a list. I'm going to delete this starting block. This is a template of, and we're going to expand this as we go on, of sort of starting sections to make it easier for you to build them. Things that represent the kind of things you might want to do. Intersecting tunnels, where the basic topology is present, but you can change it to suit your needs. And you can import this as a starting point and sort of snap them together to create whatever it is you want. I'm going to show an example of that without having to actually do it myself and fumble through it by playing back a record, which is, if you'll notice here, and I'm going to address this a couple of times, there's a state record that records all the commands you did in the course of a model, and you can replay those commands back to recreate a model state. Any interactive tool we have in the codes changes the model state by emitting commands. Those commands are in the record, and they can be either turned into a data file or replayed later. This is what I'm going to do here. So I can just type, in this case, I'm going to play it, instead of converting it into a data file, I'm going to play back the record directly. And then I can go into building blocks. Yeah. Okay, so this is a building up of those templates. Now, if that, you should be able to actually see how that was created by having the building blocks go up and down as it ran. Point is that if you hide elements, you can see internally that this was intersection of a cylinder tunnel with an intersection and a bend. Now, what you do now is you can export that directly to zones and make a save file, and that's what I'm going to do in this example, purely for the sake of speed, because I don't have time to run the data file every time. Another option, which is what we do in all our examples and basically recommend, is you can right-click on the record and say save as data file, and then you get a data file you can rerun to completely recreate that state. And then you can add to it later, parameterize it with fish. All of the data structures here are available to fish for that sort of thing. When you look at the examples in the manual, you'll see this is a repeating pattern, where the first thing you do is call a geometry data file that was actually generated interactively and stored as a data file, and you call it to reproduce that problem. Now here is once you've generated that geometry, you go to another new feature, which you've seen a little bit of just as I was playing around. This is called the model pane. So this is, once your zones are generated, this is what lets you identify regions of the model that you're going to use later on in your data file, or even operate on them directly. You can select zones by color. You can select multiple regions. You can hide regions to get it out of the way so you can find the ones you want. You can change how it's colored. For instance, here, every block gets its own group name by default, but I can change that to the ones we assigned in building blocks. You can get a better idea of what it is we're looking at. Okay. And you can go on to select regions. So in this case, let's say that I want to do a staged excavation. So I can bring up here a general range, which I can either mess with interactively or type in. Select that, and then here I'm going to give that a name, stage 1. So those have now been labeled stage 1. You can see that here for reference later when you do an excavation. Another thing you can do, if you go back here, is you can identify zone faces. So zone's fine if you're doing Wauchopa properties or excavations, but often you're doing boundary conditions, liners, whatever. You need to be able to mess with the faces. So here is a tool that's available when you're in zone mode, which is called skinning. And what that's going to do is it's going to automatically assign names to the surfaces of the model. You have some control over how that works. Note that when we switch to looking at faces, to make it clear we're looking at face instead of zone, the outline switches to white, just so people don't get confused. Now at this point, you can see that not only have we labeled the boundaries of the model, but we've labeled the internal boundaries where zone names change. So you can look at these internal surfaces and do something with them if you want. Here, for instance, I'm selecting this region of the model, and now I can just give it a name with that same tool. So I can call it, inner wall, or I can operate on it directly. In this case, I can create a 2D structural elements on those surfaces. So what I'm going to do is I'm going to say I want a liner. I'm going to put a liner on those, and I'm going to separate it automatically so that it's an embedded liner with a free surface on either side. All this is done in one operation, and you can see that command being executed right there. So now if we go to the plotting logic, we can see the liner elements that were created, and those are embedded. There are free surfaces on either side that it's interacting with. Note that all of this and everything I did has a state record associated with it, and I can save it as a data file to recreate all the naming I did and the creation of those liner elements all in one place. Another thing you can do here, if I go back to the zone view, is, for instance, let's say there I've selected those zones. It's selected by color, and if I want to just show what I've selected, you can see that. I can show everything again. Now, another operation we have, and this is just the beginning, we're going to be adding more and more operations, is densify. So I can go in here and I can say I want more zones in that wall so I can model the moments accurately. So I just replaced every zone with 3 zones in each direction. Done.
Oh my God.
So those are the kind of operations. Most of the time, what you really want to do is just identify regions of the model so you can give it a name and refer to it easily in a data file. I'm going to show you that as we go along. But the plan is more and more we're going to have direct operations so you can interactively do these things, like assign constitutive models and properties and boundary conditions and et cetera. Right now, even just doing naming is a huge benefit. So let's look at the next stage. So we've got our named surfaces, and that's, I've cheated. I've created save files ahead of time so I can quickly go from one step to another and not have to worry about making mistakes. We've got our names. So the next state is initial conditions. So now we're going to go into data file land here, and I'm going to talk about some of the things we've done to make creating a data file much, much easier. Please note that while we're committed to adding interactive tools, we are also committed to the data file. The data file is where the power is to do advanced modeling, the kind of thing you can't do with built-in interactive features. And at some point, almost always, in any non-trivial model, you're going to have to go there. And what we've committed to is making that process as easy to learn and to do as possible so that these things all work together. We have completely updated the command syntax for consistency and clarity so that every command resembles every other. The same syntax is used for the same things, and so it's much more easily human readable when you scan a data file, what's going on. The basic format we're using is noun, verb, option, modifier, range. What are you operating on? Is it a zone or a zone face or a ball or a brick? What are you doing to it? So zone property, zone initialized stresses, zone face apply, and then what option are you using for that, and then what modifiers, and then what subset of those objects do you really want to operate on? The range is a filter that says pick some zones and not others. So here's a good example of that. Zone C model assign Morpulum. The noun here is zone C model, which is a constitutive model for a zone. The verb is we're going to assign a new constitutive model, and Morpulum is the option. It's the particular constitutive model we're using. You don't have to memorize that anymore. You can, for instance, just hit F1 and come up to help, and you'll see this command interface reference index. It's quite handy. These are all the top-level nouns that you can operate on, all in one place. Zones, structural elements. We've added new nouns to make for clarity. So, for instance, everything that applies to the model as a whole has the model as the first noun. And you can just click on this to see these are all the zone commands that exist, zone face commands. These are all the model commands, things like changing gravity, etc. We've added a level called program, which is things that affect the program state as a whole. Program is a special command because actually using program is optional. We mostly put it there just to keep things in nice categories for documentation. But you can say, for instance, program call to call a data file, or you can just say call to call a data file, which is what we almost always do. Another thing that can help is once you know you want operating on zones, we've added built-in interactive tools to remind you what the syntax is. So I can hit control space here and get a nice interactive list of all the commands that apply to a zone. So I can say, oh, zone C model is what I want. Oh, zone C model assigned is what I want. Here are my constitutive models that are available for zone C model assigned. And any level at this point, I can hit F1 to get a list of more detailed documentation of that specific command and what its syntax is and what it does. For instance, I hit double yield, I can go here to the double yield model. This is a nice place to segue into the new constitutive models we've added to FLAC3D. One of the most big one is the plastic hardening model for soils, and you can see if you just click on this, you can get the full write-up and documentation of that model and how to use it and what properties are associated with it and how to calibrate them. All right here. You'll also note that we've updated the cap yield of the CY soil model. That's here. That has also been updated to be easier. So there are basically two new options for soils modeling. We have a new model for anisotropic elasticity with joint failure. So in addition to and we believe we call it ubiquitous anisotropic right here. So in addition to having anisotropic elasticity in two different directions, you can have different joint failure aligned with those directions. And then also we have something called Morpulum with tension, which is a problem with modeling tension failure in Mokulum is that you tend to get ratcheting if you've got an opening and closing path. In this case, it adds these sort of virtual faults that can open and close again without ratcheting volumetric change. And lastly, you should know that we've made it much, much easier to generate your own C++ constitutive models. And it's worth checking our website, which I should have mentioned earlier. Not only is there a complete what's new in FLAC3D here that is going to give you much more breadth of coverage than I have time for right now. But also in the Why Choose FLAC3D, you can see in the C++ plugin section a complete example of creating a custom constitutive model using the source code we provide for all our constitutive models as a base and then modifying it from there, including every step, getting it in Visual Studio, making a project from a project template, and then modifying the source to add the behavior you want. It's quite nice. All right, so once you've got your constitutive model, the next thing you do is properties. Now, there are a lot of properties. And the way we've tried to put a handle on that is you can say zone property, and then you can hit control space here. And this is the list of all the constitutive models, not properties. But if you hit like one of them, like Mokulum, you'll get a list of the properties available under Mokulum. Or you can just hit F1 in Mokulum and get this entry where you can say, I either want just the list of properties or I want a full description of that constitutive model, and move to it here. So this is the list of all the properties available under Mokulum. Same thing going with model gravity. Model is a noun. I can hit space. I can hit control space and see all the list of model keywords, things I can do that affect the whole model, whether it's cycling or solving, or in this case, assigning gravity. It's all here, and I can hit F1 to get the detailed command syntax for that. All right, so we've gone through our steps of making a model. We've created our mesh, we've identified the model regions we're interested in, and now we've assigned constitutive models and properties. The next thing is initial conditions. We've made that much easier as well. Typically, your initial conditions are stress field that conforms to gravity. So we've added a command called zone initialize stresses that looks at the density distribution in your model and gravity, and even in a fluid model, the porosity and water density, and automatically assigns a stress state compatible with that. It installs a stress ratio that you specify in the horizontal stress ratio, and you can specify different in X and Y. And in this case, we're specifying an overburden, saying that our model starts buried, so there's an overburden of 2 megapascals on top. That happens in one command. Bam, your stresses are initialized. And here, so now we've got our initial conditions. We're going to do boundary conditions. In this case, boundary conditions are applied to the faces of zones. So the noun is zone face. The action is apply. And you can see here, if you type in zone face, apply, here is all the things that you can apply to a surface of the model right now. In this case, we're just applying roller boundaries, a normal velocity condition to the west or to the east. This is something I should go back to in the model pane as a handy thing that I forgot, I'm sorry, is that if you go back to here and do that skinning operation and you tell it to ignore existing group names, you get a nice little automatic naming of your model far field boundaries. This side is called east, this side is called west, or vice versa. East, west, north, south, top, and bottom. So you can just do that as a single command, save it in your name, and then refer to them in your data file here. So I'm putting roller boundaries on the west and east and on the north and south. Note that the new apply logic resolves these multiple constraints around the corners automatically. It figures out that it's got multiple constraints and rotates the local system to adjust if it can. And here we're putting that overburden on top. We're applying a normal stress of 2 megapascals. Remember that FLAC3D uses negative for compression. And then we solve it. Note that if we've set all this up correctly, there should be no need to solve anything because we've initialized the stresses to gravity and then just applied simple boundary conditions. And indeed, it's set right automatically. It takes one step and we're done. And we're going to view that. I'm going to make another divergence into the plotting logic because this is the first time we're addressing that. The plotting logic has been updated to some extent to try and make it easier and more tractable. To add a new plot, you click on this plus, and you get the complete list of plot items available. Note that this is much smaller because we've sort of consolidated the plot items into what are you plotting on. In this case, we want to plot on zones. You can also, there's a little like quick access here for things you access frequently, and you can edit this if you want. Once you're plotting at zones, there's a question of, well, what am I plotting on the zones? So we can choose whether we're doing a label or a contour. In this case, I want to do a contour. I want to do a contour of stresses. The stress component I would look at is ZZ, and I want to do volumetric smoothing, volumetric averaging and smoothing. And that gives us the plot we're looking at. So there's this pattern we're following in the plot item organization is that there's a sort of a top-down selection drilling in on what specific thing you want. Every selection affects what's available below until you get the final result. We can like reverse this so it's highest on the bottom. Okay. Now let's go back to our data file. We've got our initial conditions. We want to do something funny, and I want to talk at least briefly about fish. So what we want is, instead of a simple overburden, we want to put some sort of geometrically diverse or complex boundary condition on the top. So what I chose is we want to, this is like non-uniformly loaded. There's an area of heavy loading that spreads out in a sinusoidal pattern and then goes out from there. So I'm able to do this very simply. First, I remove the initial apply overburden using the apply remove command. Then I'm going to write a little fish function that gives me a multiplier that goes from 2 to 1. And this gives me an opportunity to talk about some of the things we've done to make writing fish functions easier. You'll note that the syntax is fish define apply. It can take local arguments. In this case, we've changed the fish is almost all the same, but we've changed the syntax for how intrinsics are named. This is because as the code has gotten as we added more to the code, the number of intrinsics went up into the more than 1,000, and we needed to put some ability to sort it and put some control into it. This also lets us tie it into the editor and into the help system. So you'll notice, for instance, if I type zone, I can hit Control Space again and get a list of all the zone intrinsics that exist in FLAC3D right in one spot. Again, I can hit F1 and get the detail of that zone intrinsic, what the arguments are, what it returns, when it's valid, when it isn't. It's all about this. So we're using this dot, we can say zone density. For those of you who don't like that verbosity, you can abbreviate everything about the first. Note that you can also just hit F1 here. Whoops, wasn't valid. The point I'm trying to make here is that that's not valid. So the editor helps you while you're typing. If you've got a dot in a name, it recognizes it must be an intrinsic, and it highlights it in red if it doesn't recognize it as a valid intrinsic. As soon as it becomes valid, that goes away. So you know as you create your fish script whether that means it is an intrinsic or not. You can F1 here to bring up the whole thing. Again, math in this example, we've put all math intrinsics in the math category. So here's all the math operations that are available in FLAC3D right now. And you can, for instance, hit on like ATAN2 and hit F1 to get the full detail of what that is. So this helps you quickly write fish functions and figure out what intrinsics are available and what aren't. In this case, I'm not going to go over the detail of this. It's just creating a sign pattern that of a given center and radius. Now here's something new. The apply logic now has what we call a fish local. You could always apply multipliers to an apply condition. In this case, it's a locally applied modifier. So that fish function is called once for every object it's being applied to, whether they're grid points or faces or zones. In this case, it's faces. So this is called with the zone and the face separately for every point in the model, and that lets you assign this spatially varying distribution. It could also be a time varying distribution. And if we hit, now this takes about 5 minutes to solve when you run it. I'm not going to do that right now, so I'm just going to load the save file I made earlier so you can see. And if we go back to the plot we made, you can see that what we've done is added this nice little loading on the top, and this is the result of solving that in the model.
We're getting a few questions. Do you want to deal with them all at the end?
Well, no, I can do it for now. What?
So one that just recently popped up is, can you use fish functions in IPython?
We
No, we don't.
Can you use fish functions in IPython? FLAC3D 6 does not currently have Python. Well, it does have Python support. It has the generic Python support that's provided by PFC. We haven't yet added FLAC3D specific hooks to the Python. So while you can use Python scripting, in practice, its ability to interact directly with FLAC3D is limited. That is a feature we plan on adding quickly in the future, but it's not something we have support for right now. Okay, so let's move on. We've added our crazy boundary condition. So the next thing we want to do is actually excavate. Again, we've added some things to make that easier. So I'm going to show two new features we've added to the code in the process of excavating. First of all, because FLAC3D's static solver uses physics to reach the static solution, sometimes if you excavate quickly, you can cause sort of quasi-inertial effects that give you more damage than is realistic. We've added what's called it's essentially an apply condition, but we call it zone relax. So in this case, we're using zone relax to excavate that stage 1 region of zones I identified earlier in the model pane. Now what that will do is it will slowly reduce the influence of those zones over time to keep there from being a shock to the system until it reaches 0, and then it will null them out completely. Now we're going to watch this by here. This is another thing we've added, which are results files. You can see them down here as save files. Think of these as sort of stripped down save files. They only contain the information you are interested in when you're plotting. You can't restart a results file and run it. You can only see what's there. So you can control that here in the options by, for instance, saying this is how I want to auto-export. It's particularly useful in a dynamic model. You can say to export a results file every X seconds of dynamic time. You can also control what's in the results file here. So you can see that for zones, what you get are stresses, displacements, and the group assignments, and pretty much nothing else. As a result, results files are typically about 5% the size of a save file, and you can make a bunch of them without filling up your hard drive. In this case, I'm going to export a results file every 400 steps. Okay, there's been a question.
Does the apply command assign stress to the face, which is inside to the axis? Can you read the bottom question there?
Yes. Does the apply command can assign stress to the face? Yes. It doesn't matter if you apply normal stress. It doesn't matter what the orientation of the face is. It will be applied normally. You can also specify a local axis system to override the system that's defined by default by the face itself. So, for instance, you want to apply a stress that's not aligned in the direction of the face, you can do that either way. And that also applies, by the way, to velocity-based constraints. Even if the face is at a weird angle, you can fix it at the normal velocity, and it will resolve all those constraints, even in areas where those intersect. So, for instance, doing a pie-shaped model is much easier now than it was before. Okay, so let me actually execute this, and it's going to restore the save file. And you can see that what's going to happen is this region of zones here, representing excavation, is going to go less and less stressed as it's excavated out until eventually it will disappear completely.
Just reducing the internal stress in those zones?
We're reducing the stress and the stiffness and the density all uniformly to get this to.
Do you have any control over that algorithm, or does it somehow look at the...
You have a ton of control over that algorithm. That's what we do. If you go here and say, for instance, zone relax, excavate, and just hit control space, you'll see you can specify how that drop occurs. By default, it's tied to a servo based on out-of-balance force, but you can specify it as that it degrades linearly over a fixed number of steps. You can specify to use a table. You can use a fish function to control it. You can do whatever you want. It's all, that's how we roll here at Itasca. So that ends up in stage 1, which is a full excavation. All right, now here is the result of that, where you can see it. Now I'm going to do a little aside to talk about convergence issues. Note that we just use the standard model solve, which is what we call an average ratio, which means that on average the grid points are converged, but any individual grid point might not be converged. As we investigate ways to increase the speed of convergence, one of the first things we want to do is give you tools to see how that's working. And one thing we can do is we can go back here and we can, instead of plotting stresses, we can plot the local force ratio to see where, now on average it went to 1 to the minus 5, but in some areas it's still at 3 to the minus 4. Those areas correspond where the zones are small and stiff and on the surface of the excavation. So what we've done to give you some control over this is we've created something called a ratio target, which you can also plot. What that is it's what is the target force ratio that would be considered converged if you were doing, if everything had to be below that ratio to be considered converged. We were doing ratio local. By default, that's 1 to the minus 4, which in our experience corresponds roughly to, for most models, to an average ratio of 1 to the minus 5. But you can set it to be whatever you want. If you've identified a region like these small zones that are having trouble coming to convergence and you don't think that is affecting the results of your model in any way and it's not worth taking the time, you can increase the target ratio from 1 to the minus 4 to 1 to the minus 3 or 1 to the minus 2, saying, I don't care so much about those zones. They can be less accurate. They're not seriously affecting the overall results I'm interested in. And what that allows us to do is create a new convergence criteria called originally convergence. Now what that is essentially the ratio of your target to your actual imbalance force at every grid point. So model solve ratio local 1 to the minus 4 is by default exactly equivalent to model solve convergence 1. The difference is that convergence gives you the ability to edit which areas you care about and which areas you don't. In this case, you can see every place that's got a convergence of greater than 1. And a really handy way to show this is to actually do an isosurface plot, which we, by the way, have sped up a great deal. You can do an isosurface plot of convergence 1 to see every place in the model it isn't converged in 3D and where that relates to in your model and whether you care. This is a fun thing, by the way, to watch evolve as you cycle a model because you can see it like get bigger as excavations happens and then come down again. I encourage you guys to look at that and play around with this new convergence criteria. In certain cases, like where you've got extremely stiff zones in areas that you don't think are affecting the specific result you're interested in, it can significantly speed up the static solution time. Lastly, I want to look at some structural element updates we've done. So the first thing we want to do is we want to create a shell liner around that excavation and then put in cable bolts. So we've done some things to make that easier. So for the struct shell create, remember we've adopted the same syntax everywhere. So it struct shell create by face, range group stage 1. So that's going to create shells on the surface of all the faces of stage 1 in one command. And then here struct shell property isotropic assigns properties. Once we've got those shells, now we need to create cable bolts. What we've done is we've given you the ability to import those cable bolting patterns for cables or any structural elements, really, piles, beams, liners themselves, from CAD data. So you can land your cable bolting pattern in a CAD file or in the Geometry Logic Control FLAC3D or in Rhino, whatever you want, and import that bolting pattern directly into FLAC3D to create your cables. In this case, we've created a cable pattern called cable.dxf that goes around this tunnel. And every time you import it, you can offset that, so you can repeat it as we move down the tunnel, just from one single cable bolt pattern. The cable go in a group of 6, and then we give them a group name called grouted, and then here's something called snap. Now what this does is it attempts to solve one of the biggest problems we used to have with creating these cable patterns when you had a liner, which is the end of the cable had to correspond to a structural element node. So what snap does, it says automatically move the cable a little bit so that the end corresponds to a pre-existing structural node, and it'll move it sort of rigidly as a unit to make that happen. So it snaps it to an existing node. And what we can do is I'll just see if I can run that right now. Get rid of some of these things that are cluttering up the, if we make a new plot of, first we'll plot shells, so you can see that we added them on the surface of that excavation. And then we can also plot cables, and you can see where we've added them according to that pattern in 2 different places, all in one DXF. We could also plot that DXF separately, but you get the point from the cables. Let me get the cables a different color here so you can see them better. Now, this is all called grouted. Now, the next thing you typically notice that they've been snapped so that they correspond to where nodes are. Okay. So the next thing you want to do typically is you want to join those nodes. So the struct node join command will automatically rigidly join together any structural element nodes that are in a corresponding location. So that will rigidly connect the end of the cables to that shell liner in one command. The next thing we want to do is pre-tension the cables. Now, this used to be a big pain in FLAC3D involving fish to properly pre-tension. That is no longer true. What we're going to do here, we're going to use a cylindrical range element to assign an ungrouted name to the inner part of those cables, the ungrouted part, and closest to the excavation, and the grouted part farthest away. Then we're going to assign properties to the grouted and ungrouted. Same properties on both sides, but the ungrouted part is going to get 0 grout stiffness and 0 grout cohesion. Once we've got those labels, we're going to apply a pre-tension to the ungrouted region in one command, struct cable apply tension. This is what the pre-tension value to those ungrouted, and then we're going to solve it. Now, rather than start from scratch, I'm going to do something here. This is a thing you can just run selection, and it'll run those commands as if you type them in rather than have to rerun the whole data file from scratch. It's a handy little trick. Now, if we do that and we change our label, this plot, so we're actually plotting axial force. Whoops. You can see that, whoops, sorry, there we go. You can see that they've been pre-tensioned to 1 unit, more like we said, down to 0 as they go into the rock. We don't need to cycle this anymore. It'll come to equilibrium pretty quickly. And then once it comes to equilibrium, you can remove that tension, pre-tensioning value that's fixing the tension, and the cables will evolve naturally from there.
Can you attach the cables to the shell elements without snapping them to the shell node?
Yes, although it's a little harder. You can attach them to nearby nodes so that they're slaved in sequence. What you can't do, and what we plan on doing in the near future, is attach them to an arbitrary position on the element. That's something that's going to come later. But you can certainly attach it to the zone, which in many cases is good enough because the elements are attached to the zone, so it sort of falls out.
And then there are a few more questions. If you go in and look at those, I have flagged red. But one that came up is they want news on the release of version 6.
Okay. Our hope is to get version 6 released very early in next year. We're having trouble getting the documentation together. I don't know if you've noticed, but we're doing a completely new documentation set, and if you go here and see it, all the documentation set is being done in this interactive format. It is much more convenient, even if it isn't fully printed, but it's requiring us to rewrite, reformat the entire manual set, which is a big job, and it's taking us a little longer than we thought. One of the things I want to point out, though, of particular interest in this is this index of examples, which is a complete set of all verification example problems in the manual of all kinds, and there are a lot of them, sorted into categories. So if, for instance, you want an example of how you use geogrid elements or how you use interface element, you can click on this and get a complete list of examples that use that feature, and then click on that to see the whole write-up and the data file that implements it below. This is an extremely valuable resource to people trying to figure out how to use FLAC3D to apply to specific kinds of problems, and we hope to add more and more categories in the future for not just code features, but areas of application. But you'll see that this is the focus on this documentation set and its interactivity with the code itself has been something we spent a lot of time on. And the goal to make FLAC3D much easier to use. What else?
Okay, how can, and you may have answered some of these already, how can we get code for created model using extrusion?
I answered that one, yeah. There's examples in the state pane, basically.
We have someone requested an example of a FLAC PSC coupled.
Oh, I'm going to get to that.
Okay.
That's coming up next.
Okay, so I'll just clear these up so that
Okay.
you can move on. Most times we build a model with the edges parallel to the axis. Can we rotate the model?
Yes, that's actually easier now than it was before because most of the commands have the ability to specify an arbitrary local system, including the apply logic will automatically rotate to the face normal. And the zone initialize commands allow you to sort of rotate your stress state. So yes, you can do that if you want. It's still probably better not to use a system that's different than your mining system. There are a number of reasons why in general that's not a good idea. But if you need to, you can. So.
Okay, one last one right now. What changes are there to dynamic analysis?
I was going to get to that at the end, but I might as well answer that now. They're basically, aside from the various features that make it easier to create the model, two of the things that I was going to address in this presentation anyway are we've got this dynamic input wizard that allows you to specify your ground motion, your input velocities, do things like filter it, baseline correct it by a number of methods, and then output that straight to FLAC3D as an input velocity or stress field to apply your seismic waves or whatever it is you're doing. Also, for dynamic models that have large difference in stiffnesses, whether because of zone size or because, for instance, structural elements or properties, the dynamic multi-stepping option has been re-implemented to work better in a multi-core environment. As a result, models where there is a big degree in stiffness contrast, which is almost every dynamic model involving structural elements, they run much faster, on the order of 4 or more times faster than before. Those are the two improvements that come to mind right now that affect dynamic. Okay, lastly, I want to address the question on PFC. So we have integrated, and we are in the process of integrating all our codes into the same basic framework. Right now, for lack of a better name, we're calling it the Itasca framework, but I'm sure we'll come up with something better. The point is that both FLAC3D and PFC are instances that can be loaded into that framework at runtime. 3DEC will someday follow. And you can do that right now with a simple menu option, Tools Load PFC. And what that does is it loads the compatible version of PFC directly into this FLAC3D instance. Balls, walls, everything. And you can see the immediate effects of that by going to a plotting logic, and here suddenly you can got ball and wall and clump objects available along with zones and structural elements. What that does is it puts all the PFC commands available to you as well. And if you look at, we have a couple of examples of this. Here is a punch problem that is now gonna, and I'm gonna maybe set up a plot of that. So we can see. Now if I add balls, so you can see what's actually happening here. Here is a FLAC3D zones representing a punch, punching down into PFC balls, and interacting along the zone boundaries. So we can plot, displacement magnitude on the balls and displacement magnitude on the punch. That's an example of balls and zones interacting. Now note that that's all happening inside one data file, where you're using ball commands just like in PFC, and the later zone commands just like in FLAC3D, and then causing them to interact along the zone boundaries. So it's all just one model file. It's not only true of zones, it's also true of structural elements. So we can, for instance, run, this is a little small example of a scraper, which is a a group of balls, and this is not walls. This is FLAC3D structural elements, meaning it's fully deformable. It's doing the equations of motion. It's calculating forces. You can look at stress resultants. You can see the deformation of this object as it scrapes into the PFC material. And you can just cycle through this and see the displacement field as it goes. Turn the transparency off on that so you can see it better. So these are actually FLAC3D structural elements interacting with balls to do these sorts of coupled interactions between not just walls, but actually deformable objects interacting with balls. And you can have all three operating at once. If you pre-purchase FLAC3D, you can access to pre-release, and you can use it on projects. Our engineers are using it on projects. We consider it ready for that, with the caveat that it is a pre-release, so you're more likely to run into bugs than in a full release. That said, we have a full suite of tests, of verification example programs that are run overnight. We make any change to the engine. You're more likely to run into a user interface problem than an engine problem at this point, although I can't rule out either. There's much more information available on our website. If you look at the Why Choose FLAC3D and What's New in FLAC3D section. Also, we have a lot of videos on our YouTube site that give much more detail, in particular about building blocks, what controls are available and what the kind of things you can do to it. I didn't even begin to address the features available in building blocks. I did not have time to do it justice. I could have spent 2 hours on that piece of code, on that section of FLAC3D alone. So I encourage you to look at those videos to get an idea for what kind of tools are available to create meshes in FLAC3D.
You also didn't mention about the Converto tool.
Oh, thank you for mentioning it. That's very, very important, and it was on my list, and I skipped right over it. It's, for those of you who are freaked out about changing the syntax, that everything you knew before and all your data files don't work, don't worry about it. We have something we call a conversion tool. So if I go here, and I helpfully named it old to remind me, if I bring up an old data file, what immediately happens is the code looks at that, scans it, makes a heuristic check and says, this looks like it's an old syntax data file. Do you want me to automatically convert it to 6.0 syntax? And you say, okay, and it'll do it. It'll convert it. It'll save an old version up just in case. And it automatically goes from 5.0 syntax and before, because everything pre-5.0 is data file compatible, to 6.0 in one watch. Anything that it couldn't convert automatically, mostly because it needs awareness of context that it doesn't have. It highlights in orange and gives you instructions on what's going on. In this case, it says, in the new syntax, bulk could have referred to property names in a number of different constitutive models. I can't tell which one you meant, so I'm going to say it could have been any of these. Tell me which one you want. Most of the time, it's just bulk and shear, for instance. And you can just go and edit that out back to what you wanted again. In this case, it's friction and dilation. Again, the vast majority of the time, it's going to be bulk, shear, friction, and dilation, but it can't be certain, and we don't want to assume things that are incorrect because it could get us in trouble. It also converted the fish. All the fish intrinsics were converted from old to new. It does everything for you. At this point, this data file is runnable, so it's an old syntax data file, which you can see runs Prankel's wedge here is what it's running. So, so don't be afraid to throw. We've run a lot of extremely complex data files and fish functions through this by our own engineers who wanted to convert their old data files to 6.0 syntax. And while you do have to edit some of the stuff in orange, in general it works quite well and transparently. Sorry for skipping that. That's very important. Thank you. Thank you for